Hey guys, you had to know this was coming. We're getting into applying all that we've been learning about circuits to some math here. So this is going to be our assignment today, so if you need to pause and go find this, please go do so. I'm going to make a few annotations on here to hopefully guide you, and hopefully you know what you're doing when you get there, but we'll have to see. Okay, so a few key ideas. I know that they write out these equations here, but I would, again, take a couple minutes, hit pause if you need to, if you didn't write these down yesterday. These are going to be, I think, the simpler way to think about these equations. Remember power, I would have put them all on the same line, but I ran out of space. We can calculate three ways, and it's measured in watts generally, okay, but we can go work over time, current times voltage, charge divided by time times voltage, or we can use this weird unit of the kilowatt hour, which I don't think you need on this particular assignment, but again, pause if you need to. Please write down at least from here up, and hit play again after you've done that. I just have a few things to point out before we go. Zoom back in here. So again, anytime if they're asked for a potential difference, that is voltage. Voltage is the potential difference. Okay, so don't be like, what? I don't know what that is. It's voltage. Okay, it'd be measured in volts. Because remember, it's the potential, it's the difference in potential energy from one part of the circuit to another part of the circuit. That's the difference. And the only other thing that I think you really need is this idea. The hotter the wire, the more resistant it becomes to the flow of charge. I didn't think I had talked about that too terribly much, so I thought I better point it out right now because there's one question about it. We are going to try to do these two examples. I realize that they have the answers right there, but you know that doesn't mean you know how to do it, right? So let's see if we can make sense out of these two examples without using what they told us. Okay, so household current in a circuit cannot generally exceed 15 amperes for safety reasons. Okay, so we know that what did I just put that? We have 15 amps of current maximum. Okay, what is the maximum amount of charge that could flow through this circuit? So charge is our question mark. That's what we're trying to find, right? And it says, what is the maximum amount of charge that could flow through this circuit in a 24-hour day? Okay, so how do we proceed from here? What kind of formula do we have that could help us out? So we have current, we have charge, and we have time. Oh, that's not the piece. There we go. So we look back at our formulas. We're looking for one that has current, charge, and time. Looks like the top one, right? So current equals charge over time. I'm going to write out the units version of the equation down here. So that would be amps equals coulombs divided by seconds. So what's the problem with our current units that we are given? We have amps, but we're given hours instead of seconds. So we have to kind of remember back. We know that there are 60 minutes in 1 hour, and there are 60 seconds in 1 minute. So I take 24 times 60 again. I get that is 86,400 seconds. So I can plug that in on the bottom here. So I have 15 amps of current. Would go with, I don't know how much charge being moved in 86,400 seconds. So my unknown is divided by 86,400, so I will multiply by 86,400. 15 times 86,400. I get 1296000, And remember, that C is really for charge. And so our unit of charge is coulombs, which is one of those cool, I think, cool sounding units. So let's see if our answer agrees with theirs. So we got 1,296,000 coulombs. They got 1.3 times 10 to the 6 coulombs. That's basically the same. If I rewrote this in scientific notation, I would think I would keep two significant figures, because that is 1.5. It's the same answer, right? But now we know how they did it. I think their work, you know, it makes sense, but all of this signature stuff. An I is, for some reason, the substitute for current, probably because current and coulombs and charge all start with a C, so just kind of be aware there. I is current. I don't know why they went with that letter. All right, second example, we're going to again try to work through solely because I don't want to use up all, there's only 5 questions. I don't want to use up all of them going over how to do it. So what is the resistance of a heating element in a car? So resistance is what we don't know. It says, what is the resistance? In a car lock deicer that contains a 1.5 volt battery supplying a current of 0.5 amperes of current. Okay, so we look back at our equation page. We have resistance, voltage, and current. Okay, so all right, which equation is going to help us out here? Resistance, voltage, and current. That's going to be the best one. So we have voltage equals current times resistance. 1.5 volts equals current times resistance. Okay, my unknown is times 0.5. So to my 1.5, I would do the opposite. I would take 1.5 divided by 0.5. And it gives us 3. And then remember our unit for resistance is that really cool symbol. It's omega in Greek, but we would say ohms. 3 ohms of resistance. Okay, so those are the two pre-solved ones. Oh, look, we did it right. And I also want to do one more, just because I think it was a unnecessarily kind of a tough one. And that's exercise 2. And so here we go on that one. Okay, so Fabian's car radio will run from the 12 volt battery that produces a current of 0.2 amperes of current even when the car is turned off. The car battery will no longer operate when it has lost 1.2 joules of energy. If Fabian gets out of the car and leaves the radio on by mistake, how long will it take for the car battery to go completely dead? Okay, so we know 12 volts. We know 0.2 amperes. And we are given a 1.2 times 10 to the 6 joules. Okay, so we have a current, a voltage, and remember joules is amount of energy. Okay, so now what? Okay, so we're trying to find, it says how long will it take? Time is what we're trying to find. Okay, so my unknown, or my variables here, voltage, current, energy, and time. Okay, so this one has current and time, but charge, which is nowhere in our stuff. This one has voltage and current and resistance. And resistance is really nowhere in our stuff. This one has energy and time and power. So we know the energy, but we don't know the time or the power. Right? We know current and voltage, so we could figure out power. Okay, so if we use this to figure out power, then we can go back and we would know power. and work or energy and solve for time. So that's what we're going to actually end up having to do here. So I'm going to try to follow it along here. So power is current times voltage. Okay, so we don't know power. We know the current is that 0.2 amps. Voltage is the 12 volts. Okay, so 0.2 amps times 12 volts will give us 2.4 power. And our unit for power, our standard unit for power is watts, right? So now we know power, but we're trying to get to time. Okay, so now we know power, and we know the work done, the energy that is being drained from his car battery, and we're trying to find time. So I can plug in, so we have power equals work divided by time. So I can go 2.4 watts equals the work done, that's the energy consumed, 1.2 times 10 to the 6 joules divided by time. Okay, remember the cheat, when your unknown's on the bottom all by itself, it can trade places with the other side. So I'm going to go that 1.2 times 10 to the 6 divided by 2.4. I'm going to get a pretty big answer. Okay, I got 500,000. What unit of time is kind of our standard unit that we use unless otherwise specified? That's seconds. So if somebody said 500,000 seconds to you, it probably doesn't give you a very good sense of how long that is, right? So what would maybe be more useful is if I convert that to either hours or days. So I have 500,000 seconds. I know there's 60 seconds in a minute, and there's 60 minutes in 1 hour. So if I wanted to stop there, I'd go 500,000 divided by 60 divided by 60. That would be roughly 139 hours. Or I could go one further and say I know there's 24 hours in 1 day. Divide by 24, and I get 5.8 days. And that probably gives you a better concept of how long it would be before he drained his battery. So I'll, of course, accept 500,000 seconds, but remember, if you get something that is in time and doesn't really make any sense, it's always better to convert it to the best unit in terms of that. So your assignment, and I will honor Easter break, so this is your assignment for Thursday, April 9th. So it's not going to be due till 3 school days after Thursday. So that would be Tuesday, Wednesday, Thursday next week. So I would like you to do number 1, and then 3, 4, 5. As always, let me know if you have questions. Happy to video chat or whatever, guide you through them. Let me know. Talk to you later. Bye.